The Chinese Remainder Theorem is a very important theorem in ring theory, in modern algebra, and so we're going to look at a proof of it today. Now, the statement of the Chinese Remainder Theorem goes as follows. Let R be a ring, and let I1 through In be a collection of ideals of R. They have to be pairwise co-maximal, which means that any two of them that aren't the same can't be contained in any maximal ideal. Or, in other words, the sum of any two of these ideals has to be the entire ring. Now, under this hypothesis, let's let capital I be the intersection of all of these ideals. Then there's a ring isomorphism where R mod I is the direct product of R mod Ij, as j goes from 1 to n, and in fact we can say more than this. They're not just abstractly isomorphic, we can say exactly what the isomorphism is. It's the natural one that takes an element of R mod I with a certain representative x and sends it to the n tuple where the jth coordinate is the equivalence class of x inside the ring R mod Ij. So it's natural to come up with this function, but noting that it is in fact an isomorphism is where the content of this theorem lies. Alright, so let's get into the proof. So we're going to proceed by induction on n, on the number of ideals in our initial collection. Our base case is going to be n equals 2. The n equals 1 case is too trivial for us to work with. So let's suppose that n is equal to 2, and rather than dealing with indices here, I'm just going to let I and j be co-maximal ideals of R, and then we're going to try to build this isomorphism in the n equals 2 case. Let's let phi go from the ring R to the direct product R mod I, direct sum R mod j, and we're aiming to use the first isomorphism theorem to prove that R mod I intersect j is isomorphic to this ring on the right. So let's let this be given by phi of x is x plus I, x plus j, as in the statement of the theorem. Now, the function phi is easily seen to be a ring homomorphism. This is very quick to check. Phi really is just the direct product of two projection maps, which we know are homomorphisms because of the way that operations on factor rings are defined. So, phi is easily seen to be a ring homomorphism. I'll leave that as an exercise for anyone interested. So, let's get into the more interesting part, which is showing that phi is surjective and identifying what its kernel is. Let's do that first part. Let's do the second part first and handle the kernel. Now, x is an element that belongs to the kernel of phi. This is true if and only if the image of phi, which is image of x under phi, which is x plus I, x plus j, is the zero element in the ring R mod I plus R mod j. But, of course, this only happens if x plus I is equal to 0 plus I and x plus j is equal to 0 plus j. So this happens if and only if x belongs to I and x belongs to j, which is, of course, just exactly the same thing as saying that x belongs to the intersection of I and j. So this tells us that the kernel of phi is exactly equal to the intersection of the two ideals I, and j. All right, so that handles that. We've got the kernel as we need. The surjectivity requires a little bit more cleverness. So let's handle that. Now let's let x1 plus I and x2 plus j be any random element of R mod I direct product R mod j. We need to show that there's something in R that maps to this element under the map phi. Now, since I plus j is the whole ring R, this tells us that there exists y1 in I and y2 in j, such that y1 plus y2 is equal to 1. This is really what being comaximal usually means in practice. When you have two ideals that are comaximal to each other, usually the property of them that you're going to use is the fact that you can find a sum of something from the one ideal and something from the second that add up to the identity, 1. Once we have this, I'm going to define an element x which is going to do the job for us, but I'm going to show that we can write it in two separate ways. So let's go ahead and let x be x1, well, whatever element the x, choose a specific representative from this first coset here. So we'll let x be x1 plus y1 times x2 minus x1. All right, so let me just point out here that y1 times x2 minus x1 definitely belongs to I, because y1 itself belongs to I. And so this whole expression here belongs to x1 plus I. But let me now rewrite it. We have that y1 plus y2 is equal to 1, and another way of writing that down is to say that y1 is 1 minus y2. So x is also equal to this expression, but now we notice that if we were to distribute this out a little bit, we'll have x1 plus an x2 plus a minus x1. So the x1s are actually going to cancel. We're going to be left with an x2 minus a y2 times x2 minus x1. But the point here is that this belongs to x2 plus j, because y2 belongs to j. So this tells us that if we take phi of x, this will be x plus I, comma, x plus j, but that's going to be exactly x1, that's going to be x plus I, x plus j, and by the arguments that we just had, this is the same as x1 plus I, x2 plus j. So this means phi is surjective. Thus, by the first isomorphism theorem, we have that R mod I intersect J, R mod the kernel of phi, is isomorphic to R mod I direct product R mod J. Okay, so there we go. That's the base case. It shows that the Chinese remainder theorem holds when we have only two ideals that we work with. So now let's handle the inductive step. Although before we do that, we're going to prove one claim which is going to make the argument a little easier and is sort of interesting in its own right. All right. So before the inductive step, we'll prove the following claim: if I, j, and k are pairwise, comaximal ideals of R, then I and j intersect k are comaximal. So if I've got three comaximal ideals of a ring, and I take the intersection of two of them, then that intersection will be comaximal with the remaining one from the original three. So let's prove this, and once again, the comaximality is going to mean for us that you can find a couple of things that add up to 1. So let's go ahead and let x1, x2 belong to I. Let's let y belong to j, and let's let z belong to k, such that x1 plus y is equal to 1, and x2 plus z is equal to 1. This is possible by our original hypothesis. Then we can note that 1 is, of course, 1 times 1, which is x1 plus y times x2 plus z. Now, if we expand this all out, we get that this is x1, x2 plus x1z plus yx2 plus yz. And now if I look at each one of these pieces, x1, x2 certainly belongs to I, because x1 and x2 do. x1 and z belongs to I. Y and x2 belongs to I, because x1 and x2 belong to I in each of these cases. But then yz belongs to j times k. So this whole sum right here does in fact belong to I plus j times k. So in fact, we're proving something a little stronger than in the claim. We're actually proving that I and j times k are comaximal. But j times k is a subset of j intersect k. And so the statement that we have still holds. So thus, I and j intersect k are comaximal. Okay, so there we go. We've got the proof of this claim. You'll notice that we've actually proved, again, something a little stronger. We, in the statement of the claim, we could have, instead of writing j intersect k, we could have written j times k, and our proof shows that. Also, notice we never actually use that j and k are comaximal in here. So we could have a stronger, more technical statement which says something like, if I and j are comaximal, and if I and k are comaximal, then I and j times k are comaximal. That's certainly true, but that's a little bit more complicated a statement than we need here. But that does work. That does get proved by what we just did here. All right, now with this claim, we are ready to do the inductive step and finish off the proof of the Chinese Remainder Theorem. All right, so let's look at the inductive step. Going back to the proof of the Chinese Remainder Theorem. So now let's suppose that n is greater than or equal to 2, and that we know the result for n. That is, if I have a collection of n pairwise comaximal ideals, then R mod their intersection is the direct product of R mod the individual ideals, as in the statement of the Chinese Remainder Theorem. Now, let's let I1 through In plus 1 be pairwise comaximal ideals. And let's let I be the intersection of all of them. The intersection from j equals 1 to n plus 1 of the ideals ij. Now, by the claim, the set of ideals I1, I2, up through in minus 1, and then the intersection in with in plus 1 is also pairwise comaximal. And that's because if we take any two ideals in this new collection, well, if they're just regular ij's, then we already knew that that the ij's are pairwise comaximal. But then if we take one of the ij's and then this last ideal, which is an intersection, then we can use the previous claim to show that because ij, in, and in plus 1 were comaximal, then so is ij and in intersect in plus 1. So that's how the claim shows that. But now, this set of ideals with the intersection at the end is a collection of n pairwise comaximal ideals. And notice that their intersection is still I, because I was just the intersection of all of the ideals, and so it doesn't matter whether you intersect some of those ideals beforehand or not, the intersection is still just I. So, by the inductive hypothesis, we have that R mod I is isomorphic to, well, it's the direct product of R mod all these ideals in this new set, which I'm going to split up a little bit. So that's going to be the intersection from, the direct product from j equals 1 to n minus 1 of R mod ij, and then the direct product with R mod in intersect in plus 1. All right. So now by the base case, actually, we have that R mod in intersect in plus 1 is isomorphic to R mod in direct product R mod in plus 1. So this means that R mod I is isomorphic to the direct product from j equals 1 to n minus 1 of R mod ij, and R mod in intersect in plus 1, but by the base case, that's isomorphic to R mod in direct product R mod in plus 1. But of course, this is the direct product from j equals 1 to n plus 1 of R mod ij, which is exactly what we wanted. This is exactly the isomorphism that we're looking for in the statement of the Chinese remainder theorem. So by induction, this holds for all n greater than or equal to 2. And that finishes the proof. Not a terribly difficult or complex proof. You do need to know what the function is to set up that you want to use as your isomorphism, but that's fairly natural. Really, I would say the only two clever parts of the proof are in showing the claim, showing that that comaximality is preserved if you intersect some of the ideals, and showing surjectivity requires you to come up with this element x based on the y1 and the y2 inside your ideals that add up to 1. But once you have those two ideas in mind, the rest of the proof goes in a fairly straightforward manner by the first isomorphism theorem and induction. All right, so that's the Chinese remainder theorem, and I hope you enjoyed that.